How does an ultrasonic transit time flow meter work? Every good theory has a good story that goes along with it. In this case, a man and a boat. Well, this is a picture of a river. And in this river, the flow or current is going from left to right. The man wants to cross the rowboat. And so he gets in his rowboat at position B and goes across the river, carries him downstream to position A, and takes him a certain amount of time to go across the river. Then to come back across the river, he has a couple other things to contend with. One, he's going against the current, so it's going to take him a longer period of time to go back from position A to position B, and he also has to come back at an angle to arrive at the same point. So from this we've learned that because of the current of the flow, it takes him a certain period of time. When he comes back against the current, it takes him a longer period of time. The faster the flow rate, the greater the differential from the time he goes across the river to the time he comes back from the river, because he has to go against the current. Using this in mind with an installation of an ultrasonic transit time flow meter. In the picture to the right, we have two ultrasonic transit time transducers strapped to a pipe. They are installed in what's called the V configuration, where they're both on the same side of the pipe. This is the most common installation for this type of technology. The transducer on the left will send out a sound beam burst across the pipe, reflect off the back wall, and received by the transducer downstream. The electronics will take note of how long it took to transmit from the first transducer to the second transducer. Well, the second transducer downstream to the right-hand side will at the same time send a burst of sound across the pipe, reflect off the back wall to the first transducer, and the flow meter will take note of the time it took to transmit from the second transducer to the first transducer. Now, both of the signals are influenced by the arrow on the left, which is the current of the liquid. So in this case there, the faster the current, the longer it takes from the transducer downstream to get to the transducer on the upstream side. So this differential is what we used to call the transit time theory, or the differential of these times is how they calculate the flow rate on a clamp-on ultrasonic transit time flow meter. And the installation is a variety. In the lower right-hand corner is very similar to the man in the rowboat theory, where this is called a single path or a Z configuration, traditionally used in larger or difficult pipe applications, where we send our sound beam back and forth across the pipe. And then upper right hand corner is another picture of the dual path or V configuration, which is traditionally used for smaller pipe size applications. In addition to the theory of operation, where does a transit time flow meter work? Well, step one, it does need to have some straight run of pipe, traditionally about 10 pipe diameters, because you need a symmetrical flow profile inside the pipe for an optimum performance. As the diagram on the left hand side is a cutaway of a pipe. Again, say a man in a motorboat this time is at the center of the pipe, where the flow is indicated there and the wake is cast out towards the side. Well, this shape or elliptical shape does change based upon the high and the flow rates. However, it is symmetrical in that if you were to cut a center line down this pipe there, the top half of flow would equal the bottom half of the flow. Where the opposite of that is in the asymmetrical flow profile, for example, right after a 90-degree elbow. Right after a 90-degree elbow, the flow is very disturbed, and say it looks like the inside of a washing machine because it's rolling, because on the elbow there you've noticed the distances on the outer diameter is a longer distance, on the inner diameter is a shorter distance, so you get a rolling effect right after that. So we'd like to stay away from a 90-degree elbow, and you like to get about 10 pipe diameters for optimum flow performance there. The second thing that an ultrasonic transit time flow meter needs is a closed full pipe. It'll work on an ultra pure liquid up to applications that are about 4 to 5% solids by volume. A generic description of that would be ultra pure liquid to sewerage, but it does not work on sludge. Don't confuse an ultrasonic transit time flow meter with an ultrasonic Doppler flow meter. Doppler flow meters are traditionally used for heavy slurry applications, and that is covered under a different theory. Here's a brief look at traditional applications used for ultrasonic flow meter. Again, as you can see, with an ultrasonic transit time flow meter that work in an aqueous base application, whether it's water or oil, it really doesn't make any difference, or mixtures of them. The Doppler technology, again, is used for heavier slurry applications. At Instruments Direct, we don't play games when it comes to customer support. So if you have additional questions about this theory of operation or any of the products on this website, feel free to contact us at any of the numbers to the right or log on to our live chat feature on this website.